start my lecture by expressing my thanks for the extremely generous hospitality I enjoy at the Institute. In fact, I don't know, what gives me the honor to enjoy this very generous hospitality. I'm trying to enjoy it. My science is a little slow at the moment, but who knows, maybe it's going to accelerate. We'll see. So I'm going to talk about quantum mechanics, and maybe we'll go to the next slide and see. Consider credits. It's a good time, a good point to start with. So here you see the important names, first of those who invented the important ideas and concepts. In red are those people whose work I consider to be more essential than the work in blue. Now Eliot will immediately disagree. He will say Schrödinger was more important than Heisenberg, but I take the opposite view. My teachers are listed here who taught me quantum mechanics. Of course, I thought Eddie would come, so Schneider-Zehnder was his script of the quantum mechanics course of Joost. And, pardon? Oh, he's here. Eddie, you are listed. Did you see that? And Specker is listed too, who died recently. He is famous for the Cauchy-Specker theorem, of which I believe it's really an interesting observation. Anyway, these are the names. Let's go on. So here's a little abstract. I tend to think one of the problems with quantum mechanics, maybe also with classical physics, is that people usually don't try to clarify the general setting. And the hope is if you get the general setting right, things will become sort of obvious and easy and comprehensible. And apparently in quantum mechanics, it's an empirical observation that apparently that's not the case yet, because people have lots of completely confused ideas about quantum mechanics, and so I would like to try to do better by sort of introducing the right framework. So I want to do that. I would like to propose a framework that encompasses both classical theories of nature and quantum theories. And I will try to highlight what I believe are the confusing aspects of quantum theory and suggest why we shouldn't be confused about them anymore. I also think there are still lots of interesting problems in quantum mechanics that mathematicians should worry about. Nowadays we believe that it is only string theory that poses interesting problems for mathematicians, but I think that's a mistake. Even quantum mechanics is rich in good mathematical problems. All right, let's go on. So here's a little outline of this talk. I will start with an introduction, then I would like to clarify not really what the physical system is, but what the model of a mathematical model of a physical system is. I then will exhibit a few consequences of the non-commutative nature of quantum mechanics. Then I have to talk about quantum probabilities, and I believe this is in some sense the most important section of the talk. If I had time, which I'm sure I won't have, I would make a few remarks on relativistic quantum theory, the role of causality and things like that. But I'm afraid probably we are not going to arrive at that point. So let's start with the introduction. I would like to propose a few quotes. There are better and worse ones. So a good one is Niels Bohr, who said, in our description of nature, the purpose is not to disclose the real essence of the phenomena, but only to track down, so far as it is possible, relations between the manifold aspects of our experience. The one that follows is due to Weil, who worried a lot about geometry, and I think also about the way geometry would appear in quantum theory. So he revived an old point of view due to Leibniz that goes as follows. Indeed, space and time are nothing in themselves, but only a certain order of the reality existing and happening in them. This would become relevant if we made it to section 5, which we probably won't. There is something else that Grothendieck said also about geometry. It's too long to read. And now come a few quotes that in some sense I think a little silly, except for the last one. So the silly one is Feynman, who said, if someone tells you they understand quantum mechanics, then all you've learned is that you've met a liar. To some extent it's true as an empirical observation, but I think we should not give up, we should not resign, but try to understand. And Bohr said, anyone who is not shocked by quantum theory has not understood it. So I like the one by Wilson best. We have to ask what it means and hopefully find out. So what's the purpose of this talk? I will, as I mentioned, propose a unified algebraic description of classical and quantum mechanical physical systems. I would then like to clarify what kind of a theory of nature quantum mechanics is, and if we have time, say a few things about the role of causality and how space or space-time might emerge in a sort of from a general formulation of quantum theory. But the main purpose of the talk is to to make a first step towards getting rid of all the nonsense about quantum mechanics that is still circulating among grown-up people, including, physics Nobel Prize winners and so on. I mean, it's really true, unfortunately. So, what is a physical system, or what is a mathematical model of a physical system? A physical system S can be specified by or characterized by specifying the physical quantities about the system that can be measured or observed. Now, whether we consider classical models or quantum models, physical quantities are always represented by self-adjoint linear operators. That's a sort of empirical observation. And what would then be more natural than to consider the algebra these operators generate? So it doesn't mean that all the elements of such an algebra represent physical quantities, but it's sort of the smallest algebra that contains all the physical quantities. Now, there is a little complication that some people find discouragingly confusing. I think is not such a terrible thing. Namely, essentially every physical system that we want to explore is of course embedded in some kind of environment with which it interacts. That means usually the systems we are interested in are not what is called closed physical systems because of their interactions with some environment. So I should normally enlarge the algebra to something that we might want to call a kinematical C-star algebra that takes into account events or quantities that belong to the environment in which the system is embedded. And we want to choose the environment sufficiently large to be able to consider S composed with E as a closed system. To speak of a closed system means that we can represent, for example, the time evolution in terms of automorphism groups that act on this algebra Bs. All right. So here are the fundamental data that come up in the description of physical systems. There is an algebra AS generated by the physical quantities characteristic of S. It is embedded in a somewhat larger C-star algebra B sub S that takes into account interactions with an environment. We consider the space of states on B sub S, where the notion of a state just refers to a linear functional that is normalized and positive. Then element 3 of our structure is the symmetries of the system, including, for example, time evolution. And we want these symmetries to act as star automorphisms on B sub S. So an important example concerns the time evolution. With a pair of times S and T, I associate an automorphism alpha sub T sub S and S that moves an observable physical quantity at time S to time T. All right. Incidentally, if there is anything you don't understand in this jargon, you just stop me and I'm happy to explain it. So let's now introduce the notion of an algebra of possible events in the system S. It's the algebra that is generated by products of observable physical quantities A super K, moved from an initial time t0 to a time tk at which, for example, they are measured. And then you take linear combinations of such products. That's an algebra. And then it's natural to pass to the norm closure, which I denote by E sub S. In non-relativistic quantum theory, usually E sub S is a type 1 C-star algebra in the sense of James Glim. So here is what we have. We have E naught sub S embedded in its norm closure, and that is the sort of smallest algebra that can be viewed as describing a closed physical system containing S. All right? So we call it the algebra of possible events in S. So what is a possible event? Pick a physical quantity A in this algebra A sub S and decide that you would like to measure it at some time t. This is a somewhat dangerous statement because we usually don't quite know when we measure something, but I will try to clarify that later on. So I move it to time t, and then let's suppose the event is that the measured value belongs to an interval I of the real line. Well, then it's very natural to say that the event that the measured value belongs to I corresponds to the spectral projection of this operator A sub t corresponding to the interval I. I think it's very natural. And of course, everybody. In fact, I'm not going to say anything new in this lecture. I'm just trying to synthesize what people have understood in a more or less coherent way. All right, there would be an element 4 of my structure that I should clarify, but for the sake of time, I will not be precise about this. We should know what we mean by subsystems, and we should also know what we mean by composing physical systems to larger ones. That's an important theme because it leads to a notion of of statistics, in particular quantum statistics. I would like to leave this out just to save some time. All right. So now, of course, you should realize theories of nature are not nature. So our choice of an algebra of physical quantities and of symmetries and so on depends on the equipment that is available to us to observe nature. So, for example, a theory of the solar system was something completely different for Ptolemy than it was for Newton, and totally different for a modern astrophysicist than what it was for Newton. In particular, the choices of AS, GS, and so on changes with time because we learn more and more, although the underlying physical system is still the same. I think one should be clear about this. Another remark concerns the observation that the new theories of the 20th century all arise as deformations of precursor theories. And what I mean by deformation is the theory of deformations of mostly of associative algebras or of Lie algebras and Lie groups. So let's look at a few examples. One of the great things about the beginning of the 20th century was that it was understood finally and experimentally shown that the constitution of matter is atomistic. And so you can ask, do atomistic theories of nature arise by deformation of theories that treat matter as a continuous medium. Let me give an example. It's at the bottom of the slide. You can indeed view the Newtonian mechanics of point particles as a quantum theory that arises by deforming the Vlasov theory. This is, I think, a somewhat new observation that we made, but it's not difficult. It's just the idea that one can take this point of view. So atomism arises by deforming continuum theories of matter. The Poincaré symmetry of relativistic theories arises by deforming the Galilei symmetry, the deformation parameter being C inverse. Quantum mechanics arises by deforming classical mechanics. The deformation parameter is called Planck's constant, etc. All right. Now I would like to introduce a distinction between realistic or classical theories of physical systems and quantum theories. What is a realistic theory of a physical system? It is characterized by the algebra Bs being abelian. Then, of course, by Gelfand's isomorphism, I can represent B sub S as the algebra of continuous functions over a certain topological space. In fact, it's a Hausdorff space, and if the algebra Bs contains an identity, it is compact, and it is simply the spectrum of this abelian algebra B sub S. For people who like classical mechanics, they hope that M sub S will turn out to be a nice phase space. In general, of course, that won't be the case. The set of states is then simply the set of probability measures on the spectrum M sub S. Pure states are delta functions associated with points in M sub S, or if you prefer, characters of B sub S. The space of pure states has absolutely no linear structure. There is no superposition principle. The space of states has a linear structure. You can superpose two pure states in classical mechanics, but you immediately get mixtures. There is no interesting notion of entanglement. If you have a pure state of a composed system and you restrict it to a subsystem, it's still pure, obviously. If you want to describe symmetries of a realistic or classical theory, well, I told you you should look for star automorphisms or groups of star automorphisms of B sub S, and they, of course, are in a 1-1 correspondence to homeomorphisms of the spectrum M sub S. Okay, that's all these things are, little lemmas, but easy to check. Even I sort of understand why they are true. So it's not too difficult. Oh, you will see on the next transparency. So here is a little problem for mathematicians. It would be nice to talk about the geometry of classical spaces such as M sub S in purely algebraic terms. It helps the physicists if that can be done. And of course, I believe all this is worked out, but there is an aspect that I think has not been worked out very nicely, and that's the question, what is natural structure to be added to this abelian algebra B sub S that guarantees that its spectrum admits a tangent bundle? I would like to have a sort of elegant characterization of abelian algebras whose spectra admit tangent bundles. This is a sort of question zero, and I'm a little bit alarmed that mathematicians don't appear to have a ready answer, because that's what I would like to have to do dynamics. So let's look at the time evolution. It's this kind of groupoid of star automorphisms labeled by 2 times, and of course I will require suitable continuity properties in T and S. And then it should, then if M sub S admits a tangent bundle, there will be a lemma that says that these star automorphisms are generated by time-dependent vector fields. And so the whole problem of dynamics boils down to studying systems of ordinary differential equations of the form xi dot t equals x sub t applied to xi sub t, where xi sub t is a point in M sub s, xt is a vector field. So let's just assume in the following that such a tangent bundle exists and that the time evolution is generated by a vector field like here. Well, then we arrive at the realistic and deterministic description of our system in the following sense of the word. Let's look at the event. What's a possible event? The possible event in such a theory is the same as a measurable subset of the spectrum. So I look at the characteristic function associated with the subset. That's a projection, and that stands for the event that a state of the system falls into the subset omega sub I. I can move this from an initial time t0 to a time ti by simply composing the characteristic function chi sub omega with the flow from the initial time t0 to the final time ti, and that's the typical possible event in such a system. Now I can look at the whole history of such events. I can ask, and then ask what is the probability of a history. A history consists of, say, n such projections pi. I take the product of these projections and then apply a state. If the state is a pure state associated with a point in M sub s, this probability is always 0 or 1. This is, of course, the typical property of a deterministic theory and of a theory that tells us what happens and not just tells us what might happen. And that's why I call it realistic. Is this clear now? Good. So that's determinism. We could also worry about effective dynamics. If the effective dynamics would act not on operators, observable quantities, but on states, and then we immediately land on the theory of stochastic processes. I will skip details of this. Let's now proceed to quantum theories. I guess I'm doing okay time-wise. Let's proceed to quantum theories. So the only difference of a quantum theory and a classical theory is that for a quantum theory, the algebra generated by the physical quantities pertaining to a system S is non-abelian. And therefore, the algebra of possible events happening in the system S will also be a non-abelian algebra. As I already mentioned, the typical example that you encounter in the study of non-relativistic quantum systems with finitely many degrees of freedom is that E sub S is a type 1 C-star algebra. This covers the case of, for example, quantum lattice systems, quantum spin systems. It covers the case of finitely many particles where the algebra that describes the system is the Weil algebra, the algebra of Weil operators generated by momentum and position. All right. Z sub S denotes the center of this algebra, E sub S. That's, of course, an abelian subalgebra, and it sort of stands for a realistic or classical subtheory within this quantum theory. In any representation of E sub S, the weak closure of E sub S will be a direct integral over the spectrum of the center of full matrix algebras. So H sub xi will be Hilbert spaces. Xi is a point in the spectrum of the center. B of H sub xi is the algebra of all bounded operators on H sub xi. So the typical algebra that you encounter in the study of non-relativistic quantum systems with finitely many degrees of freedom has the form of a direct integral of algebras of... Pardon? Oh, type 1 means this statement, really. I mean, there are other more abstract characterizations, but the conclusion is you get these direct integrals of algebras of all bounded operators. Pardon?
I don't see where the you're doing physics, right?
I'm doing, well, I'm trying to, I usually do physics, but I'm supposed to give a talk for mathematicians. So I'm trying to speak a language that I hope the mathematicians will understand. Am I doing okay, or is there a problem?
Keep going.
I mean, you ask questions if I say something stupid, please. So these fiber spaces are Hilbert spaces. Realistic theories correspond to the special case where all these fiber spaces are one-dimensional. Then I'm back to the abelian case. So it is typical of a true quantum theory that these fiber spaces are, higher dimensional. All right. So what are the states? States are density matrices on these fiber spaces, tensored with probability measures on the spectrum of the center. Pure states are unit rays in one of these fiber spaces. And so I immediately arrive at the superposition principle. If the dimension of a fiber h sub psi is larger than 1, I can start to superpose pure states in the same fiber, normalize them to have norm 1, and I have another pure state. So in other words, there is I discovered that within the space of pure states there is linear structure, which was not the case for classical theories. Immediately I get an interesting notion of entanglement. This was incidentally, of course, a discovery of Schrödinger. Namely, I can have a system that is the composition of two systems, S1 composed with S2. I look at the pure state of the composed system and restrict it to a subsystem, and it looks like a mixture. This appears to interest people enormously nowadays for reasons that I'm not quite clear about, but there was a workshop at the university about entanglement. Unfortunately, I couldn't go. It was, I think I would have had to sign up or what. So I didn't dare attending. But I thought maybe I wouldn't miss so much, to be honest. Who knows? Anyway, so that's about entanglement. We can characterize the dynamics in these examples, propagators times flows and so on. Effective dynamics, there is a notion of quantum Markov process generated by Lindbladians. All this is interesting stuff for mathematicians, and all these remarks would deserve a separate lecture, I think. So I want to point out, I think basically just one important consequence of the assumption that the algebra generated by the physical quantities of a system S is non-abelian. And here it is. In order to highlight the significance of the remark, I should first go into a discussion of how to prepare states of a physical system. You see, a mathematician working on classical mechanics or quantum mechanics writes a sentence: let us suppose that the system S starts in a state psi naught, then what? But they never justify that an assumption that we can pick initial conditions is realistic. We have to understand how initial conditions can be prepared. I think this is a very interesting question, and I've worried about it for quite a few years, and I think I finally understand it, but it would be a different seminar, so I will not give it. But if anybody is interested, of course, I'd be happy to explain how one prepares states, whether it be in classical or in quantum mechanics. So let's now suppose I have prepared a system S in a state omega. This state could be mixed or it could be pure, whatever you prefer. And let's suppose I can measure a physical quantity A whose variance in the state omega is strictly positive. Let's suppose that after having measured A, I may measure other further quantities, A prime, A double prime, and so on. And each measurement results in some measured values. then I can ask what will be the probability of a certain history of measurement outcomes. And it turns out that even if omega is a pure state, these probabilities do not satisfy 0-1 laws. That just follows from the fact that the variance of A in the initial state omega is positive. So even if omega is pure, usually in contrast to classical mechanics or classical theories, I do not end up with 0-1 laws. And that, of course, implies that quantum theory is intrinsically indeterministic or probabilistic. All right, so that's in some sense the main consequence. I've listed some other consequences, but I don't think I have the time. I think you have a faculty meeting at 3:10, right? So I should try to, stay within the time allotted to me. So if there is anybody who has a question, you ask the question, but I won't go through this. I would have liked to say a few things about Coach and Specker, but since Coach is at Princeton, you can ask him. Or Bell would also be fun, but let's not. Let's go on. So let's now come to what I regard to be the sort of essential section of this lecture, and that is how to compute, to explain what quantum probabilities are and how to compute them. All right? The idea of probability theory within quantum mechanics goes back to, started with Born, although, of course, historians of science would say that there were other people who also played a role, but certainly Born had it in a footnote in one of his papers. And then he continued with Lüders. Lüders looked at not just at one measurement, but at, I think, 2 or several measurements in a row. Then Schwinger looked at the general sequence of measurements done on the same system in an article that appeared in the Proceedings of the National Academy, and that appears to be little known. I only discovered it thanks to my colleague Gian-Michele Graf, who is a sort of very scholarly person and discovered it. And then there was a paper by Wigner, and I will tell you what the Schwinger-Wigner formula is. It's a formula that many people have rediscovered by themselves, but they deserve the credit to have started it, I guess. So let's look at what I guess probably Bob Griffiths first called a history. Bob Griffiths is a famous name in statistical mechanics, and well, I could tell a little story about why he turned to quantum mechanics, but let's not. Anyway, so he coined the notion history. I think it was nothing new, really, but he probably didn't know the literature very well. So what is it? It's a sequence ordered according to time of observation of possible events. So every one of these possible events, pi, corresponds to a spectral projection of a physical quantity A super I observed or measured at some time ti and associated with an interval I sub little I of the real line. That is an event that possibly can happen at time ti, and it is denoted by p sub I. All right? Now, of course, when I make a measurement of this quantity A super I, the measurement can have different results. So there are different alternative measurement outcomes that could be observed. They all correspond to mutually orthogonal spectral projections of this operator A super I sub ti. And these intervals I super alpha sub I should be disjoint, and their union will cover the whole real line. I should maybe point out here, physicists do not measure numbers, they measure intervals, because measurements always have a little imprecision, and that is why it is natural to speak of not just of eigenvalues, but of spectral projections associated with little intervals of the real line.
You have several operators here, right?
Yeah, at every measurement time ti, I have a quantity ai that I want to measure or that I observe, and there are maybe n such measurements, say.
Are these projectors orthogonal to one another?
These projectors are orthogonal because ai is a self-adjoint operator and the intervals I alpha and I beta are disjoint, so the corresponding projections are all. Oh, you know, I mean, I have been told that people like these positive operator value measures, generalizing the notion of projectors. I can see some reasons why this is nice, because then positive operator value measures may belong to C-star algebras, while to get spectral projections I usually have to pass to the weak closures of my C-star algebras. I tend to think the POVMs are just there to confuse people. It's a little like Alice and Bob, you know? So I think we don't gain much by doing this generalization. But I may be missing something, but that's my present view, all right? And the sum of all the alternatives, when you sum P alpha I over all alternative measurement outcomes from 1 to ki, you get the identity, all right? So these P sub I super alpha stand for complementary possible events or observations or measurement outcomes. All right, now the question is, what does quantum mechanics predict about this? Maybe I should go back for a minute to classical, say to astronomy. You know, a very meaningful question that an astronomer who observes the night sky could ask his theory colleague would be, what is the probability that when I open my observatory at some between 9 o'clock and 9:30 in the evening, and I direct my telescope into a certain solid angle of the night sky, that I will observe Venus pass through my solid angle? It's a very meaningful question, and the guy who studied Newtonian mechanics and is able to solve the equations of motion of the solar system will tell him, well, the probability in that case will be 0 or 1. In fact, maybe it's not exactly 0 or 1, because there could be atmospheric disturbances, so the Venus will be displaced a little bit and enter at a somewhat unusual time. That could happen. Now, I think whether I'm thinking classically or quantum mechanically, all meaningful questions about nature are of this type. What is the probability that when I do observations, I find this or that result? And that is why I would like to be able to predict from my theory the probability to observe a certain history, namely a certain time-ordered sequence of possible events. And here is the master formula. Of course, to predict such a probability, I will probably have to give myself the state of the system. So I prescribe what the state of the system was at some initial time t naught. And I already made my remarks on, you know, what it means to prepare a system in a specific state, but I cannot explain it in detail because it would take too much time. So let's suppose it's meaningful to prescribe a state, and then I want to predict the probability of a certain sequence of observations. And the master formula is this formula 3. Namely, you take the expectation of the product of P1, P2, etc. up to Pn times the adjoint of this product in the state omega. This is a simple formula, and I was taught it as a student in the quantum mechanics course of Klaus Hepp. It was probably not in Schnieder-Zehnder. You maybe forgot this formula. Anyway, it was well known, and I think many people, you know, sort of rediscovered this formula. in any event, it has good properties. Obviously, the operator whose expectation value I compute, being an operator times its adjoint is positive, so these probabilities are greater or equal to 0. That's encouraging of a probability. They are also all smaller or equal to 1. Why? Because the norm of the operator whose expectation I compute is smaller or equal to 1. If I sum the probabilities of my histories over all possible alternative outcomes of my observations at all times t1 up to tn, I get 1. That simply follows from the fact that these p alphas always sum up to the identity. This gives another proof that, an individual history has a probability smaller or equal to 1. All right. And I already mentioned for realistic theories, f omega obeys a 0-1 law as soon as omega is a pure state. There is a certain symmetry between prediction and retrodiction that was proposed by Acharonov, Bergman, and Leibowitz. That is, I think, totally misleading, so I won't talk about it. And now here comes the basic problem that got people confused for the past 85 years. It's the following. Take these probabilities, fix the measurement outcomes of measurements 1 up to j minus 1 and then j plus 1 up to n, but you decide that you leave open the measurement outcome at the jth measurement. In fact, you sum over all possible alternative outcomes in the jth measurement, fixing all the other measurement outcomes. Well, then you would believe that the result should be that you haven't measured anything at the in the jth experiment. In other words, you should be able to put in the identity at the jth slot, right? If you sum over all the alternatives, it should amount to putting in the identity. Unfortunately, that's not the case in a quantum theory. It's always the case in a classical theory because all the p's commute and the sum of the pj alphas over all alpha equals identity. So this sum rule 5 is an equation for classical theories, but is usually not an equality in a quantum theory because the p's don't commute. And so that means that what you believed were complementary possible events are not events that mutually exclude each other in an experiment given a certain future. It's in fact, there is a remark, you should buy or lend a book by Weil that collects his essays on mathematics and physics and so on. And Weil has there a sentence in I think maybe it was a talk or what, that he gave before quantum theory was discovered in its final form. And he said, the present is not really finished. The present will be determined more precisely by the future that comes. And that's, in fact, in a way, this phenomenon. In fact, I was very astonished how well he understood that, although the theory hadn't really been discovered yet. So because pj without the superscript is the same as pj1. Okay. All right. So 5 is violated because of what a physicist would call interference, namely that these off-diagonal terms don't vanish. Okay. Now, of course, people here, when they go to their quantum mechanics course, they hear that quantum mechanics, has concluded peace between the wave nature and the particle nature of matter, and then they talk about interference as if it was wave interference. I think this is all totally misleading. this is what interference means, namely that this sum rule phi is violated, normally. This has a drastic consequence in this theory of quantum probabilities. There is no meaningful notion of conditional probability of an event pj given its future as soon as you have more than two alternatives. And I mean, that's easy to check. I will, maybe if I have time, will show you how it goes, but in fact it's very easy to check. In my opinion, this is in some sense the deeper meaning of the Cauchy-Speckle theorem. But I'm not sure whether, I've discussed it with Cauchy and I'm not sure whether he agrees. But anyway, that's what I think. So apparently in general, complementary possible events do not mutually exclude one another. So what to do if we have a formula that computes quantum probabilities, but it seems to be usually meaningless? What should we do? Well, we have to introduce a further concept, and this concept was in fact in some sense formulated by Griffiths, but I tend to think he somewhat missed it, the real meaning. So, but since he's not here, I should not say more because he cannot defend himself. Anyway, so it seems to me the right notion is what I like to call delta consistent histories. What does that mean? We would like to introduce a quantity that could be called the evidence for one of several alternative measurement outcomes to materialize when I do a measurement of a certain physical quantity, given a certain state and given future experiments. This evidence for a certain measurement or outcome to happen when I measure Hj is defined here. And it is simply 1 minus all possible interference terms. If these interference terms all vanish, the evidence for one of these measurement outcomes to happen is 1, and otherwise it may be somewhat less than 1. And we have to live with the idea that quantum theory is a theory that doesn't quite tell us whether some events have happened or not. It only gives us an idea about the evidence that certain events have happened, and not no certainty. And that's a fact, I think, about the theory. Now, normally in realistic situations, the evidence for a certain measurement outcome to have happened may be very close to 1, and then you can forget about interference terms. All right, so now let's say a history P1 up to Pn of n possible events is called delta consistent if the evidence for one of the alternatives to be seen in every one of the measurements is at least as big as delta for all j. If delta equals 1, the history is called consistent. In fact, this is just another way of saying that projections commute with the products of future projections. Normally, in realistic situations in the lab, delta won't be 1, but it will be very close to 1. And that's, in fact, enough, and we can even argue why it is enough. And here's a little lemma that you may want to prove during the T hour. And it says the following. Let's define Hj to be the product over the pi's from I equals n to j plus 1 times the adjoint. P1 up to Pn is a certain history. Let's suppose that the commutator between Pj, the event that is observed at time Tj, and Hj is very small in norm, smaller than epsilon. And epsilon must be small enough depending on the number of observations, little n. Then in fact there exists a history nearby the one that I consider that is fully consistent, namely all interference terms vanish. That means that the new projections pi tilde are close in norm to the given ones, the pi's, and pj tilde commutes with hj tilde, which implies that there are no interference terms. So that means in the vicinity of delta consistent histories, there are consistent histories if delta is close enough to 1. This is very encouraging because who knows exactly which operator stands for which event or observation. But if I have an approximate idea about which projections stand for which events, and if I know that I consider a history that is almost consistent in the sense that the interference terms are all very small, then by just modifying my projections a little bit, I end up with a consistent history. Now, of course, we have to understand what in the world renders histories delta consistent with delta close to 1. And that would now lead to a discussion of dephasing and decoherence. Dephasing and decoherence are very essential mechanisms in quantum mechanics. And if I don't understand them, I cannot interpret quantum mechanics. So I should probably have spent most of my time on explaining what dephasing and decoherence is. These are mechanisms that will explain why interference terms can become very small. And therefore my formula for quantum probabilities will become meaningful. There is something very strange. I think decoherence was in some sense discovered again by Schrödinger in connection with his cat, the famous, Schrödinger's cat stuff. That has something to do with decoherence. Then I think De Witt took it up and clarified what the concept means. The first more or less reasonable model about decoherence was the so-called Coleman-Hepp model, which my former advisor Klaus Hepp discussed. On encouragement of Fierz, it was written, the paper was written in, I think, 1972. He didn't quite know why he was interested in decoherence. He did not combine the idea of decoherence with the desire of having an equality in equation 5. It's very strange that this connection was not made. In fact, decoherence is just a mechanism that implies equality in this equation 5, and that's why it is important. Anyway, he brought a more or less reasonable model, and then there were hundreds of papers of people who discuss models of decoherence without explaining why they are interested in decoherence. And in fact, I find it very confusing what happened. Anyway, I could, give a short sketch of what decoherence is, but I don't think we have time to go into that. It's really, in some sense, would be a separate seminar. The important aspect of decoherence is that it's a property of time evolution, just of time evolution of the system. And I have to understand time evolution in detail to understand whether decoherence arises or not. Its corollary will be the following, that if I apply a state of the system to physical quantities of my system evaluated or measured at very late times, the state will look like an incoherent superposition of states where you have one of these projectors pj alpha on both sides of the operator tau sub t of b. I think this is maybe not quite comprehensible because I didn't go through this stuff. But in any event, it means that the state becomes essentially an incoherent mixture of states if you wait long enough. This implies that interference terms disappear, and therefore my quantum probabilities become meaningful. Now, it's probably better to look at an example. So the simplest example is the double slit experiment. you have a particle gun that spits out electrons. These electrons encounter a screen with two holes. To say that the electron went through the upper hole is an event that I call, or a possible event that I call E. To say that it went through the lower hole is an event that I call E complement. E plus E complement is everything, is the identity, if you like. Now, then after a while, I check where the electron hits the screen of an oscilloscope. And let's suppose it hits the screen of an oscilloscope in a certain measurable subset of the screen that I denote by E prime. And now I can ask, of course, I can compute probabilities. I would like to compute the probability, say, that the electron went through the upper slit and then hit the screen in this set that corresponds to E prime. And I can add to this probability the probability that it went through the lower slit and then hit in the same spot of the oscilloscope. And the question is, what is this sum? Is this sum equal to the probability where I don't measure anything in the first measurement, but I just ask where the electron hits the screen? And of course, interference means that this equality is violated. And that's what we observe when we do the experiment. Now, what is the implication? The implication is that to ask whether the electron has passed through the upper slit or through the lower slit is a meaningless question. These are not alternatives that mutually exclude one another in an experiment. And the reason is just that the interference terms are big. How can I make the interference terms disappear? Well, there are two possible ways. Either I can let the electron walk, say, through a Bose gas in honor of Elliott. Then, in fact, it will trace out the track. And then the particle knows whether it wants to go through the upper or through the lower door. But then you have to fill this half space with a quantum gas. The other possibility is to leave this vacuum, but to turn on a lamp. This was a Gedanken experiment that Feynman suggested. So you turn on a laser lamp and you do light scattering. And the scattering and then of course you include the quantum mechanics of the electromagnetic field of these photons in your quantum mechanical description. And you, in fact, have to discuss now the light scattering between light and the electron. And these scattering events tell you whether the electron came through this hole or through that hole. And interference disappears provided the wavelength of the light is short as compared to the distance between the holes. Now, you know, this is probably what Feynman said, and then you can ask, can you now do the mathematics that confirms this? And this is surprisingly difficult. In fact, this is something I have devoted essentially the last 20 years of my life to understanding problems of this type. I also have done other things, but this was one of the type of problems that I considered. The interaction of non-relativistic quantum mechanical matter with photons. If you want to understand in which way Feynman's guess was right, you have to work pretty hard and long. And it's impossible that I give you an idea of how this is done. It's just too much. But it comes out that way. It comes out that gradually the interference disappears. So you can make it gradually disappear by varying the intensity of the lamp. In other words, the interference terms do not all of a sudden die away. They gradually decrease from big to essentially zero. And it means that, you know, the idea that we know through which hole the electron came is never completely correct as an idea. There's just more evidence for the idea that the electron came either through this hole or through that hole. And all this can be quantified nicely. All right, it's almost time to stop. So here maybe a few remarks. So I would have liked to clarify the following issues, but it's just too much for 1 hour. It's not possible. So I would have liked to show how this notion of evidence for an event to have happened, given its future, is connected to the question of when does an event happen in quantum mechanics. It's not at all obvious. You see, I have always done as if I could measure a quantity at a certain fixed time ti, but that's a simplification. And I, in fact, have to ask, can we determine when an event has happened, when a quantity has been measured? Not precisely, but can I give an interval of times when it is likely that an observation takes place? And this has something to do with the interference terms and how they depend on time. And this would be a fun thing to discuss, but unfortunately I cannot do it now. But you can go to the literature and look up time in quantum mechanics. People try to introduce an operator for time and all kinds of wild things. And it's practically all nonsense, I think. But that's how people write papers. But the question is important. It's just that, unfortunately, there are very few good answers. And I think there is a good answer, but it takes some kind of, meditation, thinking. I would have liked to, tell you about realistic mechanisms for dephasing and decoherence, namely for this phenomenon that interference terms die out. But that all this would be, different seminars, and this is not a closed subject. One can still do meaningful mathematical work on any one of these questions. Here was about, cogent spectrum and conditional probabilities, but we don't want to go into this anymore. This would now be on relativistic quantum theory and the emergence of space from quantum theory and of causal structure, but that's also another seminar, I believe. And so it's, I think, sort of time to come to the end. Let me end this talk with a list of rather concrete mathematical problems. The first one I already mentioned. It's how do I prepare states in either classical or quantum mechanics? I tend to think there's been really a lot of interesting progress on this question. And I would love to talk about it, but not now. Second question is, in which sense is the idealization of closed system a meaningful idealization? That's already an interesting question in classical mechanics. If you look at the system interacting with some environment in classical mechanics, the evolution of the subsystem doesn't look canonical Hamiltonian. And so the question is, what do you have to do to justify the consideration of closed systems? Incidentally, it's also an interesting question to ask, why are Hamiltonian vector fields and symplectic manifolds better state spaces than more general things? And I think the answer comes from quantum mechanics. It's through quantum mechanics that you understand why symplectic mechanics is a good theory of dynamical systems in the classical world. All these things would deserve more attention, yeah, so you find interesting problems there. Then I already mentioned we want to have nice, realistic models of dephasing and decoherence. We would like to understand tracks. If you go to CERN and look at the particle physics experiment, particles appear to trace out tracks. How does this come about? Because, the position operator is usually not sharply defined and so on. There is no reason why a particle should leave a track in a detector. It has something to do with decoherence. Particles that move through a dispersive medium or a detector actually exhibit the phenomenon of decoherence in position space. To understand this, well, this was something that, I went a little too quick, so let's see whether we can fix this. Well, maybe we can spare the rest. No, I think I give up. So, then there is this problem of geometry. We would like, physicists would like, of course it's a terrible thing to do, but physicists would like to formulate geometry algebraically. And quantum mechanics actually, I think, poses a lot of nice problems about geometry. In quantum mechanics, the basic starting point is to talk about observers that observe nature. So they, for example, capture spectral lines from the sun and from other stars and so on. And they only record sort of scalar data as functions of time. The question is, how do you reconstruct from that the idea of physical space as a manifold and so on? So it's sort of something that I would like to call tomographic geometry. Experimentalists do the tomography of the world. They only have tomographic data, and from those they would like to reconstruct geometry. And I think this can be done. This problem is already meaningful in classical physics, not just in quantum physics. But I don't see that it has been addressed really in the literature, but I hope I will get some feedback, maybe papers. So quantum theory and geometry, I think, is sort of the, one of the subjects of the future that we should keep in mind. I think it's time to stop. I thank you for your attention.